Thank you very much for coming. It's a great pleasure to give this talk about a topic I've been passionate about for a long time. So I very much appreciate your interest. But let's start by going back in time. Like when Dijkstra started to talk about structured programming in the 60s, people would say, this is a very academic idea, and it's not very convincing. And now, nobody would think about teaching programming any other way. In a similar way, when people like Alan Kay introduced object-oriented programming languages like Smalltalk and C++, people would react with skepticism, and it's too complicated, and we don't really need that because we can do the same thing in Haskell just fine. What are you talking about? Nevertheless, today, we expect of every developer to understand object-oriented programming. Now, we are in the middle of another paradigm shift. And we hear the same things. It's all a little bit too academic, not really practical. Well, maybe some elite ninja developers can do it, but it's not for the average developer. And is it really sufficiently efficient? If I want efficient code, I write C++, right? And by the way, it's way too complicated. Look at all those Monad tutorials. So, interestingly, these things happen over and over and over again. Not just in our industry. In fact, Everett Rogers, who was a professor in communication studies, in the 60s, he already published this study, and it was corroborated over and over and over again, that whenever we have technological inventions, they spread, they're communicated through a base, through a social system in a particular way. And the dispersion of that knowledge always happens in the same way. And it's quite interesting because if you look at that model, and it's something like every business graduate would know about, I guess, is for things like railroads, smartphone adoption, dishwashers, fridges, like everything is being dispersed, diffused through society using the exact same curve. So I have to run here to show you. Like the blue curve, this is like how many new people adopt this new technology. And then the yellow curve is the sum of all the people who have adopted it so far. And it's always the same. Imagine the pattern in which railroads have spread through society is the same as iPhones. I was kind of like, really? But as I said, this has been like a business. People have corroborated this over and over again for all kinds of technologies in all kinds of societies. And it's always the same thing. It's the same pattern. So maybe we can learn something from that. So what about, we wanted to talk about functional programming, right? So what about functional programming? Where is functional programming on that curve? I would say it's, we are getting towards the end of the early adopters. And of course, it's a bit difficult how to exactly measure that because it depends on what do you call an adopter. Maybe somebody who's using React in JavaScript, they're using functional programming in some way. But that's not so important. What's important is that when you look at why and how people adopt things, it's different at the different stages. That's the important thing. So let's look at the innovators. So in our context, like programming languages. The innovators, that's the people, the programming language researchers, the people who write the first compilers, the people who write the core libraries, the platforms, the ecosystems, the people who start from nothing and create something in the hopes that other people will be using it. They are very, very happy to take risks, right? They try something and half the time it doesn't work, whatever. But the payoff is huge. If you get a thing people actually start to use, it's a huge reward, right? High risk, high payoff. Then after that, and also what's very important, these innovators, in programming languages, very often, like especially functional languages, they're typically coming out of programming language theory, mathematics, like they have this scientific background, okay? Then after that, we get the early adopters. The early adopters are the people in your team who are the first to try something. They, on the weekend, have their private project where they try a new tech, a new tool, a new whatever, and then they figure it out, and then they come into the meeting and say, hey, why don't you use that? That's the early adopters. They also take a high risk. They usually have a good connection to the innovators, and they also have the background to understand the theory, all right? But then they try to sell it to a broader group of people. And that broader group of people is what we call the early majority. And I think that the way this is relevant to this talk is that we are at the verge of where we have to think about how do we get the early majority into functional programming. The early majority of functional programmers, that is, right? Those people, they're quite differently motivated. They are not very happy to take a risk. They expect a mature platform, a mature compiler, good ecosystem, a great IDE. They want things to work because they want to solve a problem, not fiddle around with programming languages. Okay, different mindset. They're not dumber or anything. They just have different priorities. Okay. So what I want to understand, my motivation here is how do we get these people on board? Okay? So I don't know your background. Maybe some of you are in this boat. So who identifies as a functional programmer? Okay, so we're talking about you. That's good. All right, so how can we do that? Now, after the early majority come more people, but I'm not interested in those people at the moment. That's the next question, okay? Not tonight, sorry. So one reason why this is relevant at the moment, that question about the early majority, is something that Zed already mentioned, lambda clam. Lambda clam, how many lambda clams did we have? Fifth, yeah. So it's been running for a few years. And the mission statement for lambda clam was always it's aimed at intermediate to advanced functional programmers. What does that mean? Well, what it means is early adopter. People who, in their own time, on the weekend, learned how to write Haskell, ML, Elixir, whatever your poison is. And then they thought, well, I want to learn more about it. I want to get to the next level, which is why I go to lambda clam. And then I'll sell it to my team. Okay? That's what lambda clam's always been about. If you're one of those people, well, you still have a few days to think about a good proposal to put in. But what we thought about this year, we being the organizers of lambda clam, so people like that, is, well, maybe it's time to move into different demographic. So that's why we've got this Welcome to Functional Programming Day. And the idea here is that a day of workshops and tutorials will go a lot slower than the normal talks. We'll start from very basic understanding of things and allow people who are maybe not among the early adopters of functional programming. They may be early adopters of something else, I'm sure, but functional programming is not their thing. That's fine, but they think, well, maybe it's time to learn it because everybody's talking about, everybody's starting to use it. There are all these job postings offering like Haskell developers for whatever. So maybe I should think about this, right? So we want to do something for those people. And so that again leads to the question of how do we teach functional programming to the early majority? And so what I'm going to do, and on the 21st of May, I'm going to run an introduction to functional programming for people who haven't done any functional programming. People who are software developers, who know how to program, but who don't know Haskell, who don't know OCaml, who don't know Erlang, right? And any other language I've not mentioned. And then that we need to solve that problem. I need to solve that problem. But not only me, I mean everybody among the early adopters who wants to get a broader community going needs to think about that. And that's what I'm going to talk about. Now, this is on the background of, as Chet mentioned, together with Gabriele Keller, we've been teaching functional programming to thousands of students at UNISW, from first year to postgraduate students, so people who haven't done any programming to people who are quite happy to write any program in C++. And we've experimented with all kinds of ways of teaching it and what works for different people and so on. We've done a lot of student surveys to get feedback, optimize the way we are doing things. And so at one point we wrote the textbook, Introduction to Just Computing, but using Haskell. And then lately we've kind of went back and through all what we've learned, and we've developed a Haskell tutorial, which is called Learning Haskell. It's free, it's online. It's got screencast with live programming, and for all the people who didn't put the hand up when I asked, are you a functional programmer? This is for you. We've written this specifically for you. And this is the kind of material which I will also be teaching on this Welcome to FP Day. And that's what I want to talk about is what are the lessons we learned which went into this tutorial and are also going to go into that workshop on the 21st of March. Okay? So, oops. Why did I start with this whole diffusion of innovation? Well, one thing which becomes very clear if you ever become a university professor for any reason is different people learn differently. And a lot of that you can put down to that curve. And some people, the way you teach one person will make no sense to another person. And if you're a good teacher, you have to understand how to teach who. Otherwise, you won't be effective for everybody. So, two things about innovators, which they get wrong. I mean, we are not going to, I don't want to teach the innovators because the innovators are gone. I mean, functional programming has been invented. No need to teach those people anymore. They do something else now. But they've shaped the initial teaching and they've made mistakes, and we have to identify those mistakes in order to change the teaching to be more effective to a broader group of people. So what are these mistakes? So one common mistake you see in programming classes, programming and programming languages classes all the time. Lecture number 1, programming language construct number 1. Today we do while loops, tomorrow we do method calls. So the curriculum is oriented at language constructs, right? And that's really, really bad, but everybody does it because it's the simplest thing. If you being told, teach a programming languages class, well, that's the first thing everybody comes up with. It's not good though, because what you really want to teach are the concepts. Sometimes they are tied to a programming language construct, sometimes not. And this paper by Feleisen, Findler, Flatt, and Krishnamurti, they wrote this paper, they've studied teaching programming very deeply, and they've wrote this papers, The Structure and Interpretation of the Computer Science Curriculum, which every kind of die-hard old functional programmer will recognize as a play on a textbook called The Structure and Interpretation of Computer Programs. They identified this as one of the primary problems, and that really programming courses have to focus on concepts. And the syntax, the specifics of the language have to be secondary, very important. So that's a common problem. You see that all the time. Second problem is innovators. They did the innovation, right? They went a long path to finally to come to a solution. And the immediate thing for them to explain that solution to somebody else is to explain the path. But the path is not important. The goal is what the student is interested about. So one of the very popular things in the Haskell community is, like, you know, there's this mathematical domain called category theory. Who knows about category theory? All right. And who understands it? Okay, that's good. At least we've got one. No, somebody else raised their hand, sorry. Okay, so there was a really, he's still alive, sorry. There's a very smart mathematician, theoretical computer science, by the name of Eugenio Moggi. And he deeply understands category theory. And he used that mathematical, very abstract theory to invent a new way of doing formal semantics for programming languages. Awesome work. Another brilliant scientist took that work and saw, well, we can't just model programming languages, we can actually use that to structure functional programs in an awesome way. All right? It's really nice. So that's the history. And then when people want to explain how to do this type of functional programming, they go like, you know, there are these things called monads, and they're from category theory, and everybody runs away. And they go like, but that's how they were invented. But nobody cares about how it was invented. They just want to know, why should I even know about it? Right? So that's why we have this semi-joke in the Haskell community that a monad is just a monoid in the category of endofunctors. Do you need to know anything else? Yes, because we have to explain things from the viewpoint of the student, not from the viewpoint of the innovator. That person has already understood it. That's not a useful explanation. Okay? Two things we shouldn't do. Don't use the syntactic constructs of your programming languages to structure your curriculum, and don't do this with anything, not just category theory. All right, that's so much for the innovators. The early adopters, they deal with this stuff, no problem, because they're early adopters. They want the challenge and they want to figure it out so they can tell it to somebody else, and everybody else goes like, you understand that? Wow. Right? That's the payoff for them. And when they then are being tasked, and some people go like, okay, please teach me, I mean, how did you get to this awesome knowledge? Then they want to teach it the same way they learned it. And they go like, yeah, you know about category theory, here's a book. And everybody goes like, whoa. So they teach from that abstract domain. Background programming language theory. That doesn't work. Like everybody else, everybody who's not a programming language researcher or enthusiast of functional programming, particularly interested person, they want to start from examples. Why should I do this in the first place, right? So what we need to do, the right way to teach, is to start with the why, not some abstract stuff, which may be glorious, but it's not appropriate at that point in time. Then you have to have a bunch of examples, and then from those examples you can generalize to what's the problem with all these examples. And then from that, you can come to a solution, and then you do the same thing a few more times, and then suddenly you can come to the abstract concept, because then it makes sense. Then the student knows why you are doing this in the first place, other than torture them with category theory. Okay? So that's why it's important, and I like to say this, especially in the context of functional programming, because people go like, functional program, I wasn't good in math at school, and so functional program isn't for me. No, that's not the point. Math comes later. Math is great. I like math. But it's not where I start teaching. Okay? So, in fact, it's the other way around. If math is so useful to functional programming, then functional programming must be a good vehicle to teach math. Right? I mean, if it's not useful, if we can't motivate it from the functional program, then can't be that relevant. And actually, this is not just my strange idea. Who knows about this bootstrap thing? Eric. So they are the same people who wrote this paper I mentioned earlier, so Fell-Eisen et al. Or not the same people, some of the same people, and people building on their work, the work they explained in this paper, Structure and Interpretation of the Computer Science Curriculum. They developed this bootstrap program exactly on this premise. They said, if functional programming is so close to math, and we've got all these kids in high school, especially in lower social economic regions in the schools, they have a very hard time teaching STEM subjects. You all know that. Can't we solve that problem with programming? If we get these kids into programming, and they see those structures and they understand that these structures relate to some more abstract way of thinking, maybe they understand that that more abstract way of thinking, which you usually call math, is actually useful and not something to torture them with homework and mindless questions, all the same, just different numbers. And it worked. So this is still hugely successful. So what they did, they got quite a few grants and so on. And then they went into high school. So they did this over several years. They started small, bigger and bigger and bigger. And they went into especially schools in, as I said, lower social economic regions, students who really had problems with STEM subjects, and then taught them programming. And they did the usual thing you do with kids, like program games. But you want to program a game, right? You want something to fly like this. Oh, what's this? Well, gravity. I mean, do you know how a ball behaves under gravity? Yeah, well, we have to talk about how that works, right? And that way, they've got those kids to really be interested in algebra. And their algebra scores, not just their programming scores, their algebra scores went up. That's success in my book. So I just put that out there as a data point for this works. In fact, I've been saying for quite a while, when everything is said and done, right, with functional programming, then the biggest contribution of functional programming is going to be that it's going to have brought programming math closer together. But not by everybody becoming a mathematician and then learning to program. No, by all the programmers understanding these structures much better because it's part of their thinking in a natural way, not top down, bottom up. Okay, but we'll see. In 10 years, we are going to talk about this again. But there's one thing. So, talking about category theory again. Another critique which you hear about functional programming, which I want to reject, is like the jargon. People go like, you've got all these fancy words. Well, every programming language, every community has their fancy words. Do you know what a protected, abstract, virtual, base, pure, virtual, private destructor is? I have to read it off because I can't remember it. Do you? I mean, if you're a C++ programmer, you should know. But you don't, probably. I mean, except for the guru, whatever. So, of course, you learn something new. There are new words. The important thing from the teacher side is to explain all the things properly. But don't be scared of jargon. And there's a big advantage to learning the fancy new words. Because, like, look at all those words. Do you know what they have in common? Well, he knows. All the people laughing now. They've been proposed as alternatives to the word monad, which supposedly is so scary. But it's bad to replace monad by burrito.
Why?
Why? Because we want people, when they learn, after they've learned what this thing monad is, whatever it's called at the time, we want them to be able to go back and read existing literature. We want the beginner to be able to become an expert and talk with other experts. That's pretty hard if you don't talk the same language. So you have to learn the language so you can talk with everybody else. Right? Access to existing literature, other people, is just much easier. And at the end of the day, what's hard is not learning the word. Mine is pretty short. I mean, I'm sure my 9-year-old can spell it. It's the concept which is maybe difficult. Okay? So it's really, I know the words are sometimes scary, but they're not the obstacle. So that's something I reject, to rename everything. We can discuss this at some point if you like. I mean, challenge me by all means. All right. So now I've said mostly things which we shouldn't do. So how do we want to teach the early majority? What's the right way to do this? Well, there are a few points I want to make. First of all, we start with examples. We already talked about this a bit. Then the other thing which is really important is to give people patterns, idioms of how to do things. It's not good enough to explain a general mechanism and then expect everybody to be able to use that to write programs. You have to give people more guidance. We'll see examples about that. And then tight feedback loop, something which functional programming has always been good at, but we can do better. And finally, visualization can go a long way to make things clearer, especially in functional programming. Languages, once you do computations without side effects, visualizations become so much more useful because they're much closer to what actually happens. So let's go through those 4. Okay, so recursion. Recursion is usually the first problem. When you teach functional programming, recursion is the first stumbling block. Even for people who've never programmed anyway, but even for experienced programmers. Because in most programming languages is something you use sparingly. But in functional programming is basically everything you do with recursion. That's not just if then else, right? So that's kind of the first culture shock. Now there's a very simple way to explain recursion. Not simple for the person who has to understand it. It's basically incomprehensible, I tell you now. But simple for the person explaining. This is recursion in Haskell. This is all. That's it completely. There's nothing else to be said. From a mathematical point of view, that's it. That definition encapsulates the meaning, the semantics of recursion in every single programming language, including C++. That's what Eugenio Moggi showed us. Okay, done. No, not even he, like people before him. Isn't it nice, elegant? It's so small. But what is totally confusing, it makes no sense. So that's wrong. But do you know how many people I've seen teaching functional programming going like recursion is this fixed point combinator? Everybody goes like, what are you even talking about? Goes home. So, okay, that didn't work. Let's try a different way. So first of all, what did I say? Before you start with a concept, with a solution, you have to introduce the problem. What are we solving here? Why would we even be interested in recursion? I mean, we've got loops, why do you need recursion? So, example. Well, very simple example. Let's say we want to write a function called netSum. Gets one argument, n, and it's going to add up all the numbers from n to 0. Okay? So, I mean, we can write it out. So netSum from 0, like, I mean, you can do the other infinitely many lines, no problem. I trust That's easy enough. Haskell, this is Haskell syntax, by the way. You see Haskell syntax, very simple. But you may notice there's commonality. So we can do some reuse, right? We can reuse netsum 4 for 5 and 3 for 4 and so on. So then we get that. So what we notice now is everything but the first line is the same thing, except for the number. And I mean, you all know programming. So when you have a number, always changing everything being the same, you use a variable, right? So we use a variable and only 2 lines left. So that's a recursive definition, all right. Now, that's a very simple recursive definition. Basically looks like something you could have seen in primary math or somewhere up thereabouts. So actually, so the youngest person I taught functional programming to was my oldest son, who was 9 at the time. I thought that's a good time, because that's the time when in school you know how to read this. And that's basically all you need to know to learn functional programming. So it's not hard. In fact, so the people who wrote this paper and do this bootstrap curriculum, in the paper, read the paper, they argue or they explain why learning for somebody who can't program, learning functional programming is actually easier. And I've noticed this over and over again. First year students, the people who struggle with functional programming are everybody who's done some programming before. The people who have never programmed, they go like, why is this hard? So another thing is what we want to do. We want to, not only do we have examples to show how we arrive at a recursive definition. I mean, it kind of is a little bit of a recipe how to get there. We also want to see how it works. And that's so nice in functional programming, because there are equality signs. So one thing is the same as the other. So we can replace one by the other. That's the point of equality, right? So we can replace that by this, by this, by this. I think you can imagine how this goes by now. And then we get the final result. Okay? So that immediately gives you an idea of what's the execution model here, because we've just done the execution model. It's not very hard. I mean, my 9-year-old didn't have trouble understanding it, at least. But the point here is there's no point introducing an abstract idea like recursion. The only way to do it is to go through examples like this and build up intuition bottom up. Right? So, so this recursion example was very simple. Right? But that's on purpose, because I didn't want the example to be challenging. I want the example to be trivial. But the exact same method we use for all kinds of things. We explain recursion like that. We also explain higher order functions like that. That's already a little bit tricky. We explain parametric polymorphism, whatever that is, and type classes, and even categorical structures. So that's the monads and functors and all the fancy things. All that can be done in the same style. And you don't have to start with, well, a monad is, once you start with this sentence, you're lost. That's it. Everybody's running away. Start with examples. Okay. So that was number 1. Examples first. Second one is, it's always one thing to explain something like this, like everybody understood this example, but then I give you an exercise and you have to do it yourself. And you know this situation, you've got this editor screen in front of you, empty, one blinking cursor. So many letters, right? So where do we start is always the question. And that's where patterns come in. And that's something which also the people who did the bootstrap program and that paper and also a book which I'll show you later, which they are very, very strong on, is you have to give people structures of how they can. And when I say patterns, it includes the kind of OO design patterns, but I mean it in a much more fundamental way. It's really, what are the idioms in which you approach problems? So there are usually different problems which all can be solved in a similar way. And you have to tell students what are those categories, and for each category, A, how do you recognize which category your problem falls in, and then once you've identified the category, how do you solve the problem in that category? That's way easier than just empty screen, no idea how to even start. So one thing which is totally super important in functional programming is, of course, the following. So we've got a function here. It takes a list, it iterates over the list, and then for every element in the list, it's going to multiply the element with itself. Notation pretty similar to what we had before, so maybe kind of makes sense, right? It's plausible. Now we have another program, looks quite similar. I mean, the name of the function is different, forget the type signature. Then it's all pretty much the same except for the variable names, except the function we call on every element. Well, these are two different functions. That's the only thing which is really different. I mean, two different names I regard to be superficially different, right? We could rename it. That's the real difference, is the highlighted bit. So we can say, well, there's a general pattern of functions like that, where only the orange bit varies, right? If you're a Haskell programmer, you go map. Right, sure, okay, forget map, because that doesn't tell anybody anything. If you show them those two programs and you show them, there are lots of programs like that. Whenever you have this problem, well, that's the structure. You only figure out the orange bit. Then, instead of having an empty screen, you have a screen full of letters, except for the orange bit, which you still have to figure out. That's a better situation. Feels much better, right? You don't start from nothing. You start from a skeleton, and then you fill in bits. Way simpler. Way more approachable. So, of course, we have later on in your teaching, you get to, well, actually we have these higher order functions, blah, 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 blah. We are not there yet, okay? So you talk about the structures, and then you get there later. You're not talking to early adopters, remember. Okay, so spot those computational design patterns. That's how you teach recipes to how to approach various types of problems. Okay, that was number 2. So how about the tight feedback loop? So that's where we get into tool territory. So this is part of a screencast from this tutorial, learning Haskell. So we are writing this function netsum, but this time we don't do it on a few slides, but we do it in an interactive system which can actually run your Haskell programs. And we start with the same thing we did before, right? We write it out. We only write out, I think, 3 cases. No, 4. Okay. And then, in addition to writing out that program, we also get the results of running that program at the same time. And we can evaluate it for 4, 1, 2, 3, 4, and 50 doesn't quite work because we haven't given the rule. Okay, so then we get to the point where we do what we spotted before, right? We can reuse the equation in front of the current one to define the current one in a recursive manner. And as we rewrite this, you see on the right-hand side, the stuff runs all the time. So you immediately see the results didn't change. Right? We rewrote this program, results doesn't change, it must be the same program, right? Same meaning. And then at that point we spot that all the equations are the same except the first one, so we can introduce the variable and then just have the recursive definition of netsum. And lo and behold, not only does everything stay the same, but the call with the argument 50 also evaluates, because now it's recursive and works for every number. Okay, and that's for at the beginning of your teaching functional programming. That's how people can approach actually writing these functions, to write out examples, just list them out, and then find the commonalities, comment it up, and that's how you get to your recursive definitions. Way easier than trying to get at it right from nothing. And probably you think, well, I could have come up with this. I'm sure you could, because you're all experienced developers. But believe me, when recursive functioning has to get more complicated, you are all going to come to a point where you go like, ooh, and this is going to be much easier than trying to write it out. Okay? All right, that's what I mean by tight feedback loop. You write the stuff, you immediately see what happens. You can experiment, you can play around, you can change things. There's no wait time, compile, execute, whatever. All right, and visualizations can be very effective. So again, recursion is perfect for that. So who knows about fractal trees? So the idea is you start with a square, and then you draw a circle on top, and you take the Pythagorean theorem. This is why the trees have that name. And so you get a head on the tree, and that's where you draw the next box, like that. And then again, and again, and again, and again. Looks pretty recursive to me. But this is basically a visualization of binary recursion. Okay? So let's do this in code. So this is pretty small for you, because the screen is so far away. Well, this is going to be the recursive case. So this is just a list with one element. So what we get at the beginning is just the stump, right? So, and then what we do, we just add one recursive call to that recursive function fractal tree, but instead of with n, we call it with n minus 1, and we adjust the baseline, depending on the triangle on top. And now if we increase the recursion count, we get this list-like straight structure. And now if we take that recursive call and we add another recursive call of the same kind, only for the left part of the base, then we get a tree-like structure which kind of illustrates binary recursion, and by increasing the recursion count, the tree grows. So that's a very simple way to illustrate recursion and make really clear what happens. And you can do nice things. I mean, this is the same code, only with some parameters changed to make it a little bit more fancy. So you can do kind of interesting graphics with that. So again, and that's recursion, but it works for many other things as well. As I said, once and in functional programming, a lot of computations don't have side effects. It's the values, the result values of functions which count. And that makes it very amenable to draw these structures, right? Like you could draw a list structure, a tree structure. And I think, I mean, in my experience, this works well. It builds a good intuition in the students. All right. So that's the four things I wanted to go through. Start from examples, teach the idioms, the patterns with which you start to write programs, tight feedback loop, and visualization as helpers. So I want to touch on one question which comes up a lot, at least among people who teach or think about learning functional programming, and that's, do you want a type system or not? Like, this is, you take a random group of developers and say, do you want a type system or not? Fight! Works every time. So, what's a type system? I mean, to answer that question, other than fighting, no problem, we can fight if you like, but if you want to answer it without fighting, then maybe the first question you should ask is, I mean, what's the point of a type system? Take us? No, Eric is not going to answer. Anybody who is not a hardcore Haskell addict. Pun? Pun?
Group things together.
Group things together, yeah, yeah. But why would we do that?
Avoid illegal values.
Pardon?
Illegal values.
Legal values, yeah.
Right.
Yes, to make illegal programs unrepresentable.
Yeah, so that's a very good way to phrase it, make illegal programs unrepresentable. So usually people, you're a very sophisticated crowd. A lot of people, they just tell you, well, the compiler tell me what I can't do. I get an error message. If it's wrong, it's wrong. But then other people come like, do you want the compiler to tell you what your program should look like? I want freedom. I only write Python. Okay, Ruby these days, whatever. So there's this notion of a type system is just something which is going to restrain you, right? It prevents you from doing things. That's bad. I mean, that's what your parents did to you when you were little. Why would you want to go back to that, have this compiler boss you around? But I think there's a fundamental wrong understanding of what the point of a type system is. Type system is not there to police your code writing. It's a design tool. You have to use it. It helps you. It's not there to. It's like you use tools. If you want to draw something, if you're an architect or so, and these days you draw on a computer, but before you draw on a computer, you had tools to help you draw straight line. You didn't think, this ruler, I will not accept you because you only allow me to draw straight lines. Right? So we have to, and this is not, I mean, this is a totally separate topic. How can you use types to help you design programs? I can give a separate talk about this, so I can't go through that. But that's what's important. And it's not only me who is saying that. So there's this book, which is by those guys who've mentioned a few times. So who wrote this paper? Actually, this paper is about the approach taken in this book, which then led to this bootstrap program. And interestingly, so the programming language they use is Racket, which is a dialect of Scheme, which is a variant of Lisp. So it doesn't have a type system. But if you read the book and you see how they explain how to design programs, that's what the book is about. The first step is you start with examples. So we are on the same page. These people and I, we are on the same page. You start with examples, and then they say you write down a type signature. And because it's Racket, you write it in comments. But still the second step, you write down the type signature, because after you've got the examples, you know what your data is. The point they're making is you structure your code by the data. Data comes first, then code. That's what every person who is in favor of type systems will tell you. But they say just from a design point of view and teaching programming point of view, that's what we found is the best approach. And if your compiler doesn't understand your types, well, at least you put them in comments. So I thought that's quite interesting. And in Haskell, you can write down the type signature or not, because Haskell has type inference. So if you don't write it down, the compiler figure it out itself. But if you write it down, what you get is the compiler tells you if you made a mistake. If the type you wrote is not the type you wanted to write or not the type your code has, it tells you, well, maybe think about it again. That's a help, right? If you don't want that help, well, don't write down the signature. But it's good practice. That's what they're saying in this book. I mean, read the paper. Reading the book is interesting, but, well, it's very basic. It really is for beginners, so it's the basic for you. But the paper is good because for people like you. And if you really want to know how to use types to design program, well, I gave this talk at YOW Connected 2 years back, and it's online, and there's a video, and it's not about Haskell, it's about Swift, and it'll tell you how you use types to design programs. So there's that. That's the separate talk, which I can't give now. All right. So at that point, then nobody raised this objection, but you're very friendly. You don't want to challenge me. Thanks. So people go like, but when I prototype, when I experiment, I mean, the types get in my way because I write my program, then I want to refactor, so the types are not right, I can't run anything in the medium term, and so on. And then I say, which planet do you live on? Because this is something which is a property of the implementation. It's nothing to do with the language or whether the language is strongly typed or not. So let me prove that to you. So we've got another small example. Here we've got too small, sorry. the data type definition of a tree, expression tree, having multiplication, addition, and integers, and that's a small evaluation function. Now here in this example, it only returns always an int, because we only have addition, multiplication, and integers. Now we add another operation, equality, and then we got another possible result type, namely bool. All our types are going to be wrong. Yeah! So we add equality into the picture, all right, and then we have to think about what's the result of eval now. Well, it can't be int, because must be something else, and we define what's called a sum type in Haskell, so one thing or another. It's an alternative disjoint union variant. Okay, and we change our function definition here, and from expression to value, immediately we get a type error. Now, the thing which we were worried about happened. Now, this is just to allow it to print these types. So there's this type error. Nothing works anymore. All the examples which previously worked, errors. Okay, well, let's try just changing one of the equations, right, for one case. So if it's just an integer literal, we just return the integer. Oh, look at this. Suddenly, that example, which only covers the case of only one integer, it actually runs and returns the result. There's still a type error. I mean, we've got a type error. Doesn't mean we can't run our program. So, oops. Now, this is the type error. And if you look at the exception here, you see it's the same thing. So what we've done, we've deferred the type error. So what the type error means, if you actually insist on running this program and you take the code path which involves the code where the type error is, then you get an exception. That's like in Python. Only you still have static type system. This is not mutually exclusive, right? It's a matter of the implementation. And then we changed another, so the case of addition, we changed that. And then maybe we are not quite sure what we do this case, we pattern match on the results, and we're not quite sure what we should put in as a result of this equation now. Like, what's the right thing? So we can just put an underscore. And then what the compiler will do, it will tell us what the type is which is expected at the place where we don't know. This is how types help us write programs, because it tells us this must be of type value. Well, type value, there are only two alternatives. Must be one of the two, can't be anything else. Well, addition gives me an integer, so now at this point there's only one possibility left, right? So I put in that only possibility, int val, and then maybe I don't know what's next. Put in another underscore. We call this a hole. Put in a hole, and then ask the type error. Tells me, well, this is must be an integer in the result, and there are two variables which are of type integer. So I got to use those, because how will I get an integer otherwise, right? And I want to implement addition. I know that. So I have two integers. I just add them. Let's see what happens. Okay, so we've got that as a result, and we only got these two variables which are of integer type. We add them, and lo and behold, now this second example, which only uses addition, runs. The third example doesn't run yet, because it still has a type error, because it involves multiplication, right? So we change that around too, and everything's fine. So having type errors and having the ability to experiment, these are not mutually exclusive things. It's just some implementations aren't sophisticated enough to allow you to do both at the same time. This is an implementation problem. It's not a fundamental conceptual problem. Okay? Right. And that brings me to tools. And now I'm going to really aggravate everybody. Because I think, like we talked about structured programming, object-oriented programming, now we are functional programming, so we have made a lot of new a lot of progress in programming languages, but people still use all the editors they've been using. Well, I added Atom, so there's a new one in there, right? We still use the old tools. Our tool chain is still the same. Like, there are two options. Either it was perfect right from the start, VI was already the end of all there is, or we've overlooked something. So, just as food for thought, go to this website. Who knows this website? It's from a person called, whose name is Brad Victor. He's a very big thinker. And just look through these. He's been thinking a lot about what should programming environments look like. How can we improve them? Is what we got really the best we can do? And he has great ideas. Some of these things are quite clear how you can scale it to large things. I think we can quite easily use it for teaching, but how to scale it up, some of that's not quite clear. And that's why we got researchers figuring stuff out, innovators, right? The innovators, that's the next thing the innovators can do, right? And there, for example, there's this group at Y Combinator Research who are experimenting with some of those ideas. So they have this kind of teaching environment which they propose for kind of somewhat weird language, where you get a lot more feedback, a lot more information while you write your programs than you're usually used to, right? And the programming environment I've been using, which obviously is for Haskell, it kind of also tries to very slightly push in this direction by having these playgrounds where everything you type is evaluated as you type it. You change things around. You get feedback not only on type errors, but or completions, like the usual things your IDE or even your Emacs after you've spent 3 days configuring it gives you. You also get things being run. And especially for people learning, this is very useful. But once you get used to it, actually, even as an experienced programmer, it's also easier, right? So this works quite well. We've used, so this thing is on the App Store. People like it. We've used it for, so we being Gabi and myself, we've used it for a few years in classes at UNSW. It's just like you don't want to go back, because it's just clearer what you're explaining if you don't have to switch between your editor or buffers in Emacs and then type something in GLCI. Now, functional programming languages, since Lisp, they had this idea, of the REPL, of the interpreter loop. And this is the first step. It's much better than just a compiler and a .a out and run that, right? REPL, way better. But playgrounds, even way better than a REPL. Right? And I mean, bigger people have realized this. So Apple has in Swift, for Swift Xcode, the Apple IDE, it has support for this same kind of playgrounds. And they even have this app on iPad, which is called Swift Playgrounds, and it's specifically for teaching. And they are using that, they're teaching. So Apple is teaching a lot of teachers who are now tasked, like everybody says, kids should code, learn to code at school, blah, 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 blah. But how? Same problem. We talked about this earlier today. And Apple is giving courses on how to do this in, well, you guessed it, Swift, and using stuff like this iPad app. And really makes things a lot easier. So you already noticed, I mentioned earlier, I use my children as guinea pigs. So last year, after we did some Haskell previously, so now he's a bit older. He's 14 now. And not this summer, the previous one, when that app was out new, I told him, okay, this summer, what we're going to do in the summer break, we're going to go through all the tutorials in Swift Playgrounds. And he went through everything and was good. I mean, there are some criticisms I have, but the basic premise, I mean, they put in a lot of work, very clever design. And so this year, in the summer break, we wrote an entire iPhone app together. So this stuff works, right? He's understood enough Swift programming that we could do something real together after that. So all I'm saying, like, I'm not the only crazy person saying, maybe we can do better than VI. I'm sorry if you're a VI user. I do use VI sometimes, okay? It's good, but it's not the only thing. All right, so, so the main point, when you teach actually everything, but functional programming, specifically functional programming, start from examples. It's so tempting because the beauty about functional programming is the abstraction mechanisms are glorious. And so once you're experienced, once you know that stuff, it's so easy to start with that. And that's really the downfall of so much functional programming teaching. And if you want to get broader acceptance, it's not going to work. Start with examples. Give people idioms by which they can start to construct their own programs from building blocks rather than starting from nothing. And then we should think about better tools. Now, better tools is nothing which you need for functional programming. I mean, you can use VI and Emacs and everything, and enough people have learned functional programming like this, perfectly possible. But because of the lack of side effects in functional programming, a lot of this tool support, I think, can go even much further. Right? A lot of things where you need a source code debugger with complicated state and introspections and everything is much simpler in functional programming. All the things about testing with mocking and all this stuff is basically doesn't even exist. Right? So functional programming, in a sense, is way simpler. Right? So, and if you're interested, you or somebody you know, to learn Haskell, well, go through the tutorial. It's online. You can just do it with VI if you like. Thank you very much.